Good evening, everybody. Hi, Miss Joan. I'm just want to welcome Dr. Sue Ziegler from Memorial University is going to be joining us this evening to talk about climate change.
Now, you seeing the title slide okay?
Perfect.
Okay, great. Well, excellent. So this is great to have an opportunity to sort of have a bit of a chat and overview to talk about how our natural environment actually has been reducing the impact of our emissions. And what I mean by emissions, I'm talking about release of greenhouse gases, such as carbon dioxide, into our atmosphere, which is having an influence, obviously, on our climate. And kind of put this into the context of ongoing climate change and also the initiatives that are underway by our government here in Canada, as well as other governments across the globe to sort of meet targets for reducing these emissions. So this 50% discount that I have here in the title slide, I'm hoping becomes sort of, is understood kind of at the end or throughout the talk. And what I'm referring to is that we've got these natural ecosystems in our environment that have really cut the amount of carbon dioxide that we've been putting into the atmosphere in half. And so some of the work that we do in my group is actually involved in understanding how some of these natural systems are responding to climate change in kind and what might happen to that discount that we're enjoying. Before I get started, I do want to just acknowledge the fact that I've had the honor to work within ecosystems and also working here on campus and so forth, which is really on the traditional territories of a lot of indigenous groups within the region, including the Beothuk, Mi'kmaq, Inuit, and Innu. And Julia put out a sort of a little blurb about this particular panel session, I guess, and had, mentioned about net zero emissions. And so Canada, like many other countries, has sort of joined on to this international agreement to get to what's called net zero emissions by 2050, not very far off into the future. And what that net zero refers to is we're talking about basically getting to a point where we're either not releasing any carbon dioxide or greenhouse gases into the atmosphere, or if we are emitting some, we are applying some kind of mechanisms. We're using some kind of management of ecosystems or some kind of technology to recapture the same amount of what we're emitting, so that basically on a net sense, kind of like a bank account, we're actually not increasing the reservoir or the bank account of carbon dioxide in the atmosphere, and that we can allow natural systems to bring that down further. So this net zero is a very important target. And you kind of want to ask yourself, well, how are we doing in Canada with regard to this? And this graph here, trying to think if you can see my pointer, is actually showing the amount of carbon dioxide per year that was projected to have reached. So what kind of annual emissions is Canada as a whole putting into the atmosphere, given various periods of time where different kinds of policies were put into place. So before any of the climate plans here, we're looking at something on the order of 800 megatons of CO2. And as these frameworks were put in place, these are sort of what the benchmarks were meant to be. We're meant to bring down, basically by 2030, bring down those emissions from the original 2005 level by 40%. That's a lot. From 2005 annual emissions by the time we get to 2030. Well, where we are within the last couple of years is right here on the second dotted line, indicating that on our way to getting to 2030, we've only really reached about 25% of where we would like to be relative to what emissions we were putting out back in 2005. So we got a lot of way to go, and many of us have heard this in the news, obviously, about these lofty goals and how we're going to get there. So we don't have a lot of time left, but there are measures that we can put in place, obviously. And some of the conversation around some of these measures that has entered into the conversation is this use of natural-based solutions or management practices that we can actually put into play, particularly in agricultural and forest settings in our environment here in Canada, that may be able to enhance the uptake of carbon dioxide and reduce maybe the emissions of these greenhouse gases that would naturally occur. And so there have been many studies, and here's one really good example that's specific for Canada. And a lot of these have been put together to try to get an estimate of how well, these management approaches might help us in our goals. And it really looks like it may help a little bit at the end of the day, maybe 11% of what we need to get to by 2050 might be able to be brought about through these management if all goes really well. But we don't really yet understand how these ecosystems, including those that we may be able to provide some management strategies for, are going to respond to future climate change and maybe alter their ability to take up carbon dioxide and other greenhouse gases. So the impact of carbon dioxide, when we think about these emissions and having an impact on our climate, is actually kind of an old story. And we do, there's a lot of work that's been underway for quite some time about trying to understand how increases in carbon dioxide in the atmosphere are going to influence global temperature. And those estimates actually surprisingly haven't changed a lot in about 100 years. So the story actually really comes from some quite old observations by some pretty sharp people. Savant Arrhenius, for example, had conducted some experiments and published this work in 1896. And he used a lot of really straightforward and well-founded physical parameters to estimate what doubling carbon dioxide in our atmosphere would lead to in terms of temperature change. And his estimate based on those is about 4 degrees. And this is not really different from the more precise measurements or estimates that have been made over the last decades since 1908. Really telling us that the fundamental physics behind this particular mechanism of what greenhouse gases like CO2 are doing in our atmosphere is really well founded and understood. What's interesting about this particular story, though, and it's not just Savant Arrhenius, but there were others that he was citing, like Langley and so forth, was that there wasn't any citing, and up until about 10 years ago, there really wasn't an understanding that there were experiments even prior to that. So Eunice Foote, for example, is an American amateur scientist that worked back in that day on many types of experiments, and she actually had a report not read out by herself, but somebody else at the American Association for the Advancement of Sciences, really indicating and demonstrating the role of greenhouse gases on controlling temperature. Like the quote here from her work says, an atmosphere of that gas would give our Earth a high temperature. So this is this unrecognized, group of individuals working on these big problems, and I think it's important to sort of play to tell these stories and get them out there when we find them. And this came out in like the New York Times recently as part of an obituary, which is really interesting. So Eunice, as well as Savante, they had really uncovered the physical basis of what carbon dioxide does. Again, this is not the only greenhouse gas, but it's a major one that we are putting into our atmosphere. And it physically works in the fact that the low wavelengths of radiation coming through just pass right through our atmosphere, and CO2 doesn't interact with it. But what carbon dioxide actually does is it interacts with the radiation coming back from the surface of the Earth. And it absorbs that radiation and re-radiates it back to the Earth. So in a way, it's sort of recycling what would normally be lost out into space and allows for increased heating. And so it contributes to the heat budget of our planet. And so this is why we see and can also calculate what the impact of an increased carbon dioxide atmosphere would be on surface temperature on a global scale. And records of carbon dioxide have been going on for some time. There's some fantastic records off in Mauna Loa out in Hawaii. And this was started by Charles Keeling back in the late 1950s. So we have this beautiful record that continues today. And you can find this online through the Scripps Oceanography Carbon Dioxide Program, linking up all the different types of records. So this is a direct record taking measurements from the atmosphere and telling us what our carbon dioxide concentrations are. And so I checked it a few weeks ago to talk about it in class, and it was, I think, 417. So off this chart, ppm, so that's parts per million. And this is kind of interesting. So I'm going to put this in the case of like in time. So we're talking about like 70 parts per million of carbon dioxide in the atmosphere increase over about 50 years. Now, if we go back in time even further, like way back in time, and we look at what people are investigating millions of years ago, and there are all sorts of different types of records, but one type of record comes from looking at these microorganisms that were buried in sediments. They lived in the water column, but they're preserved over millions of years. And folks will look at different elemental compositions to get a recreation of atmospheric carbon dioxide concentrations. And when they do that, they can actually tell us a lot about what's happening way back in terms of the atmospheric composition. And that was really helpful because it kind of tells us a little bit about where we're headed. But it's also helpful for us to put into perspective the change in this atmospheric carbon dioxide in our atmosphere, the rate of that change that we are now ourselves experiencing. So for example, going back in this scale, unlike the previous graph that I just showed you, which was over just something of 6 decades or 5 decades or less, this is in millions of years and goes back into the Miocene and the Pleistocene and periods of very different climates. So glacial periods and then what we call warmer or optimum periods. And what's interesting to note here is that, you know, when we go back in time, so I'm 50 years old, when I was born, the CO2 concentration was about 325. Okay, and we're kind of comparing it to what these records are in the past. And if we look at what it is today, we've actually seen a change that is something on geological scales. Like this is a change that we're looking at concentration difference between an optimum warm period and basically the end of a glacial period happening within my lifetime. So that rapid change is something of great interest today and understanding, and really underscores our need to understand the Earth system and its responses to these changes. Other records that have been out there for understanding these carbon dioxide changes come from ice cores. And so we have an abundance of information stored in ice caps, particularly at the Antarctic and Arctic poles, the Greenland ice sheet and the Antarctic ice sheet. Places where the deposition rates are really, really low. So they're places where, you know, a core that you see here in this picture can be drilled, and these are kilometers long, but within those kilometers of ice is captured hundreds of thousands of years of deposition of little bits of snow that gets packed down and forms the ice. And in those little tiny layers are gases that are trapped. And so when the core is extruded out and actually divided up, folks have actually looked at the gas concentrations in these bubbles to enable a recreation of what carbon dioxide concentrations were back in time. And the ice core records that we have today actually go back as far as 800,000 years, which is really amazing. And it's really interesting, and if we look at the interglacial and glacial periods, that is the cold periods and the warm periods, because the Earth has gone through lots of climate change. Just in this more recent geological period in Earth's history, we can see those cycles, and they really just bound back and forth between these concentrations of carbon dioxide. So basically about 100 ppm during those different cycles, and just stays within those bounds. But today, we are basically, when we follow the changes that occur with carbon dioxide, and we match these up with records of temperature during that period, we can see that there is this nice matchup. So periods of higher CO2 are associated with warmer periods and so forth. And so the question becomes, when we look up here, these are the concentrations that we're experiencing way up in the far right corner of the slide. You're going the wrong way. The change in carbon dioxide that we actually are experiencing now. And so when you go back to that amount of carbon dioxide I was showing on the very first figure, we're talking about a much faster rate. So within about 100 ppm in 70 years, instead of 100 ppm in 50,000 years. And so we're talking about a much faster rate of CO2 increase in the atmosphere. So this really, for lack of a better word, or an unused word, an unprecedented, when you look back in geological history, it's not necessary, it's not the concentration, because the Earth has seen higher concentrations than we have today, but it's the rate at which we're getting there, and what it might mean for our climate and climate system. So the recent changes, like in that first graph of the carbon dioxide I showed you from the Keeling plot, they call it, which is from Charles Keeling from Mauna Loa, is shown here, which is a nice average value for the globe in carbon dioxide, is nicely matched. So 1960 to the late 2000s, you see that trend, and it's matched up with these observations of mean annual temperature. So this anomaly means that these are increases above zero. We're looking at increases of temperature relative to this period of time of the 1960s to 1990s. So when we depart from 1990, we start seeing this increase. And then these are all the various projections for where we might head with temperature, given the best ability and knowledge that we have about the Earth system in response to changes in this atmospheric composition of CO2, atmospheric concentrations of CO2 in the atmosphere. So each of the last 3 decades have been successfully warmer at the surface than any preceding decade since records have been good enough to know this, which is about the mid-1800s. And so we have a nice kind of direct record, in addition to these really nice geological records, linking this atmospheric carbon dioxide or atmospheric carbon dioxide concentration to global mean temperatures on Earth. So the interesting thing about carbon dioxide in the atmosphere and our emissions, so here is a sort of a figure of major releases and uptake of carbon dioxide happening on the globe. And of course, our activities, our use of fuels for energy, heating, and so forth, are generating almost 9 gigatons of this carbon dioxide, carbon in the atmosphere. On average, it's a decent rate even for today. And so that rate's going up and down depending on activity, but it hovers around that value. And that we don't see that much actually ending up in the atmosphere. We have really good numbers on what we're putting out there, and we have really good numbers on what's actually in the atmosphere. And we know that the atmosphere is only growing every year by about 4. So about half of what we release is actually observed to be increasing, contributing to an increase in the atmospheric composition globally. And that is because we have these wonderful natural sinks in our environment that are taking up a tremendous amount of carbon dioxide from the atmosphere actively every year. And so we have this really nice discount that we're getting. It's like a 50%, if not more, discount. And, what I wanted to do is to talk about what these suspects are, or maybe solutions is a better word. So what are the solutions? Where does this come from in our environment? And so it really comes from stores, right? We have these natural, diverse stores of carbon that has been derived from carbon dioxide in our atmosphere. So for example, in the marine environment, we have sediments, so all this like beautiful organic matter in the sediments, or we have vast amounts of biomass in seagrasses or algae, as well as calcium carbonate and biomass stored in coral reefs. On land, soils, wetlands have a tremendous amount of soil carbon, as well as vast amounts of biomass. So there's lots of these solutions, these stores, if you will, that we have throughout the world that have actually been very responsive, unbelievably responsive to our release of carbon dioxide to the atmosphere. And this can be depicted by looking at, on the top side of this graph, where everything above zero is indicating the contributions every year. So this is a cumulative amount of carbon dioxide, not cumulative, sorry, this is the rate of carbon dioxide that's actually increasing attributed to fossil fuel release, and then in the brown here is land use change. So for example, if we clear areas of the forest and burn that for agricultural use, that ends up being released and increasing the release of carbon dioxide to the atmosphere. So it's been increasing as we've been more and more active as communities on Earth. We've been pumping more carbon dioxide in the atmosphere. So the rates, or the flux, if you will, that is the amount per year from the entire globe, has been increasing steadily. No surprise there. What's interesting though is that the rate of uptake, so the sink, if you will, for that carbon in the atmosphere has also been increasing. So the oceans have, from what we understand, and we have better predictions when we get into the 1960s, have actually been increasing their uptake of carbon dioxide over all that time, and so have land systems as well. And there's a lot more variability in the land sink. And so thus, when we look at what actually ends up in the atmosphere in this light blue here, we only find about 50% of what is actually being released is actually ending up in the atmosphere on an annual basis. And so that really formulates this sort of discount that I was referring to. So it's really great that we actually, at the same time that we've been releasing more and more, the systems on our planet have actually been taking more and more up. Now, our challenge, when it comes to this, is trying to figure out what these systems are going to do as the Earth continues, as our climate continues to warm. And so we use a lot of projections. There are different types of models that are informed by our understanding of these systems on how much carbon will be taken up on an annual basis by the ocean, and how much carbon would be carbon dioxide would be taken up by the land systems. And you can see there's a bit of variation here in the projections. And so there's some measurements in here, but these are all projections. So there's a whole bunch of them here. What's interesting is the ocean is shown to continue to be taking up carbon dioxide, but most projections indicate that it's going to level off. And this is because of the pH change in the ocean as a consequence of it taking up more carbon dioxide. And so we may not be getting that any more growth in our discount. So it would be good if we stopped releasing as much and get us back down to net zero. But in the annual, when we look at the land flux, it's the uncertainty is massive, and there are many reasons for that. And some of the research that we do in my group is trying to uncover a little bit of this. So in some of the models are showing that there's an increase in that sink, and it's also going to level off. And then we have others that actually show that the land is going to become this major source. And these have all to do with our uncertainty around some of the mechanisms and reactions within the terrestrial ecosystems. So lots of uncertainty there, but we do know that we've been getting this discount, and it continues to grow. We're just not sure further on out with climate change what the change might be in that discount. So what do these solutions, these climate solutions, or these suspects, these ecosystems have in common that allow them to take up this carbon dioxide that we are releasing? It really comes down to the fact that you've got primary producers who are involved in taking up that carbon dioxide, combining it with water, and making biomass. And it really has to do with what happens with this biomass and dead organic matter that comes from the organisms themselves, in order to understand to what extent it remains a sink of carbon and continues to take it up. Because it can also be, this reaction can go back this way through the process of respiration. So when we eat, for example, and we utilize biomass, of course, we're respiring and carbon dioxide is going back. And microorganisms do the same thing with plant material, for example. So the net result, really, when we're going in this direction from left to right, is a net result of a sink or uptake of and formation of organic material in the environment. And we all love organic matter in my group because that's what we're really interested in, understanding how stable it is and how it's responding to changes in climate because of the role of these important sinks. And the direction and the amount of that sink, how much the land is taking up or how much the ocean is taken up, is really the difference between two massive fluxes when we look at it on a global scale. So really, it's all about a very tiny difference between the amount of carbon dioxide taken up by photosynthesis and the large amount of carbon dioxide that's released by these ecosystems through the process of respiration. And so that very small difference is what really is leading to this net sink of these ecosystems. And it's not only that release of carbon dioxide comes from respiration, but also forest fires is another good example. So right now, the Canadian forest, the entire area of, say, Boreal forest of Canada, used to be a net sink on a global scale for carbon dioxide. And right now, in the last couple years, since about 2018, it has converted to a source because of the intensity and the area of fire. And we don't know how long that will last, but that has converted that particular sink, unfortunately. So the biggest fluxes we have for carbon dioxide between land or Earth's surfaces and ocean and the atmosphere come from photosynthesis and respiration happening in the ocean and happening on land. So when we think about all that carbon on land, for example, most of it is trapped in soils. Soil carbon is a reservoir of carbon that's something on the order of about 3 or more times the amount of carbon dioxide that we have in the entire atmosphere. It's very large. Most of it is actually, a lot of it is concentrated, like the dark colors you see is the highest concentrations of soil organic carbon. You find it in northern parts, the cold places. And that sometimes seems counterintuitive, but the reason for that is it's not lost as easily. Warmer temperatures, you got more respiration, more breakdown of organic matter. Colder temperatures, it gets stored more easily and is held there and over longer periods of time. So we do wonder oftentimes if we warm up environments like these northern areas, if they'll become like warm places and have less carbon, and we lose that storage. And that's a big question out there right now to see what might win out in a warmer world. And the projections aren't great because when we look at different scenarios, like a somewhat of a decrease in our emissions versus like business as usual, we can see that those higher latitudes where a lot of that carbon in soils is stored is actually in places that are projected to be some of the warm areas that experience some of the greatest warming. And that warming is going to continue, and it's going to exhibit interannual and decadal variability, and it's not going to be uniform. But the general picture that we get from almost all projections really is that it is going to be more intense in higher latitudes. And these areas are where we have all those stores, like lots of rich stores of carbon, whether it's in the Arctic, like these areas, or in Newfoundland. And I get this all the time. People are like, there's soils? I thought it was just rock when you're in Newfoundland. But yes, we have these really beautiful soil profiles in the forest ecosystems across our province. And so really these stores are under scrutiny. We're trying to figure out, well, how are they going to respond as these ecosystems shift in response to changing climate? So warming of a forest and it's all the environments there, obviously is going to lead to microorganisms that live in these environments and utilize the organic matter in these environments to speed up their activity, and they're going to respire more. They're going to release that carbon dioxide back to the atmosphere, and that can be a significant input to the atmosphere for sure. But at the same time, those microbes are also cycling and making available more nutrients because they help to break stuff down. So they're going to make it more rapid, nitrogen and phosphorus, for example, more rapidly available for the plants in that ecosystem. And so that could increase plant productivity, which could increase their uptake of carbon dioxide. So warming can increase uptake and it can increase loss of carbon dioxide, depending upon the balance amongst these different kinds of reactions that are going on in the ecosystem. So for us to try to find out more about like what's happening with these stores in our neck of the woods here in Newfoundland, Labrador, about 10 years ago, I set up and collaborated with the Canadian Forest Service and the government of Newfoundland and Labrador's agri-foods and forestry group. as well as some other collaborators, to set up a series of study sites within watersheds. These are hydrographic regions like the Grand Codroy area, the Salmon River area, and the Northern Peninsula, as well as up here around Cartwright in the Eagle River area. And the reason these areas were chosen is accessibility and working within communities there, but also because up here we have the most northern extent of the balsam fir type of forest. So we're trying to stay within the same forest type and try to get the most southern area that we had good access to and the most northern area that we had good access to, and to explore essentially what's happening with soil carbon in those systems. And that enabled accessing those sites, allowed us to set up equipment, sampling regimes, and so forth to look at within the forest, but also to explore the headwater streams draining small forest areas to sort of connect it into the aquatic environment as well. What was great about exploring across this region is that we had a really nice gradient of both temperature and precipitation that is in line with what has been predicted for the next 100 years in the region. So that, about a 5-degree warming in temperature and about a 50% increase in precipitation. So we're kind of trading space for time. So trying to look at these different areas and compare them to one another to figure out what might be happening to these natural climate solutions, if you will, or these organic matter stores. So we looked at inputs. We followed what the trees were putting into the soil, and we collected soil samples, and we did studies of CO2, of carbon dioxide release, and also looked at solute or water fluxes going through the soil and how much carbon was being carried in those. And we put all these kinds of measurements together over years of study to try to understand what the fate of these surface soils might be as we get into this sort of warming kind of zone from 0 to 5 degrees, or the increases in precipitation. And what we found, not surprisingly, is this very large increase in carbon dioxide being released from the soils. Also, movement of the solute carbon through the soils. So an increase in that flux, or that rate as well. But we also saw increases in the inputs to the soil from the plants. So that was increasing as well. And by studying the chemistry of the soil, we actually did understand to a large extent that in the surface soils of this system, there seems to be the maintenance of soil stocks, of carbon stocks. So despite the fact that there were lots of carbon being lost, both to the atmosphere and through solutes, water carrying through the system, we actually see that the soil carbon stocks in some horizons are increasing a little bit in the warmer, and overall being stabilized by the increased inputs, which is good news in those environments. Well, we live in a very wet place here in Newfoundland, Labrador. We're on the sort of wet end, the very wet end of the boreal forest. And this is depicting black spruce, but it fits for balsam fir. The extent of this forest type across Canada, you can see that out in the western areas, there's very, very low water, but we're in the very wettest part. And so this could mean that the carbon stores that we have are really like a refugia in a warmer world, that there's enough water to support productivity and increased inputs of soil carbon into these ecosystems. So water availability is a big deal. It's going to dictate to a large extent, as we get into a warmer climate, that availability of water is going to dictate the fate of these large carbon stores in these high latitude ecosystems. So that maybe in our part of the world, it's possible that carbon could be sequestered. It may increase, it may be maintained, and we're trying to learn more about the deeper stores to see if they're going to actually contribute more to storage in this region. And how does that actually compare to drier areas as we get into warmer climates, where we might suspect those to become greater sources as a consequence of fire, and as a consequence of the reduction in activity to recycle nutrients, and therefore a reduction in productivity, shifts in those ecosystems as a consequence. So water availability is a big deal, and it's actually predicted to change as well as temperature, and very much so in these high latitudes where we are, and in further northern areas. And so those projections, again, are concentrated in those regions and tell us that there's going to be more variability and a greater amount in a lot of areas in terms of the percent increase in precipitation. And one thing that we know from looking at the records in our region is that we're definitely seeing evidence of increases in the size of precipitation events. As we know from just over a week ago, with getting 200 millimeters here in St. John's, and we had an atmospheric river event, meaning a large, over 200, about 250 millimeters around the Codroy Valley area last November. These events are increasing in their frequency and their size. And this is something that we really need to get a handle on to understand what that impact may be on carbon stores. So it's temperature, it's amount of precipitation, but it's also the form of that precipitation and the intensity of that precipitation. When we're out in the woods in this area, right, we got lots of snow at certain times of the year, and this leads to a lot of important part of the water input to these ecosystems. And as water goes through these ecosystems, we see a lot of organic matter moving with it, going into deeper zones, being carried into the aquatic environment. So snowmelt's a big part of our, of the dynamics in these ecosystems, and it mobilizes carbon, but it might do it in different ways. And we're trying to understand a little bit of how the dynamics of snow may be contributing to changes in where this carbon is and how much. So for example, when we look at records of dissolved organic carbon per catchment area per year, and this is just taken from the Humber River, we see pretty clear evidence that there is this creeping up of concentrations, of export of dissolved organic carbon. And this is really much in line with a number of river systems in northern latitudes, that there is this increasing dissolved organic matter, this terrestrial organic matter coming into these river systems. And we wondered about what the mechanisms might be for that and how it could or may not, whether it is or not linked to climate change. And by studying the mobilization, the movement of that organic matter in solutes in our forest ecosystems, we're able to uncover the importance of the changing winter conditions. So along this transect of sites that we studied, we actually noticed that, in this region, winter is the big difference in temperature, right? That's when we see the biggest deviation among these regions in our area. And of course, that leads to differences in snowpack depth, but also how long the snowpack persists in the area along this transect. And so when we look at this organic matter from the soils being mobilized, so the rate at which it's happening, so how much of that's actually being moved every year, we look across our study sites, so the reds in the south and the blues in the north and the purples in between, but regardless of which region in our study sites you see here, we have a pretty decent relationship with the amount of that soil organic matter being moved out through solutes and the number of days that the snowpack persisted in that environment. So with shorter snowpack season, so like just snowpack being there for a shorter period of time, we see basically higher amounts of carbon being released, and longer snowpacks led to less release on an annual basis. And we wondered, well, is this just because maybe with smaller duration, it's associated with periods, years where we had lots of rain rather than snow? When we look at the amount of water available, taking out the total precipitation and how much might be taken up by plants, we don't see a relationship. We looked at the total amount of snowfall, no relationship. But when we looked at winter temperature, just like with snowpack duration, that's what it's related to. So it's this decrease in the snowpack that's led to more of this carbon moving out of these ecosystems. So increased winter temperatures and a reduced snowpack enhances that availability of soil carbon and water to move it, right? Like it's really making those stores of carbon more vulnerable. And this might be because during a real winter where we have that snowpack, if that snowpack's on there for a long time, it's insulating the soil and the microbes are really happy. So there's organisms in the soil that are living underneath that snowpack and they're active. They're chewing away and they're removing that organic matter themselves. They're changing the nature of that. And so it means when the snowmelt does happen, there's less to be mobilized, less carbon is lost. But also the other aspect that could be happening here is that when you have a big snowpack for a long time, there's more of it that runs off, and it runs off more directly than going through the soil. And so maybe those stores are not being removed as much. So that winter period is really important and having a big impact on soil carbon dynamics in ways that may explain why we're seeing more carbon down in our streams and rivers in some parts of these higher latitude forest ecosystems or landscapes. So the mobilization of that carbon from the landscape, if we look, now we go back to the global scale, how does that actually compare to these sinks that I was talking about? So in the last little while, last 10, 15 years, these sort of global carbon budgets have been updated to include the transfer of carbon from these terrestrial landscapes into the aquatic environment. And it's large, and it might explain the larger variation that we see in the land sink, because we hadn't been accounting for that connection between the aquatic and the terrestrial environments. And so we have to ask ourselves, you know, part of this carbon ends up in the sea, but a lot of it doesn't. And we need to understand the fate of that. Is it buried somewhere? What controls how much of it's buried? Because that's an important solution, or basically a part of that discount that we're getting on our emissions into our atmosphere. So how will this terrestrial to aquatic flux change with climate change is something we're really interested in. We want to know what the fate of it is, right? Is it actually being buried, or is it actually being returned back to the atmosphere, and what controls that? And what is the impact downstream? So is this actually going to impact our coastal environments or our downstream aquatic environments in ways that are significant to various resources that we rely on? The boreal forest, you know, our landscapes here in Newfoundland are part of this boreal forest band that runs globally around the Arctic. And it contributes to these huge watersheds. And the mobilization of that carbon is getting into high latitude coastal environments, and it's significant, and it looks like it's going to grow. So what we're learning about these landscapes is really important for understanding that. And in those boreal environments, we have lots and lots of water. It comprises a huge proportion of the landscape, and it means that there's this intimate connection between the landscape and the aquatic environment, such that carbon that's coming from the terrestrial environment into the aquatic environment, this is like the upper Humber River. You can see the nice dark color here. That's dissolved organic matter from the terrestrial environment. And it could lead to processes within the water that would lead to release of carbon dioxide, or it could just be transported to downstream ecosystems or used by organisms or buried. There's lots of things that could happen to it. And that dissolved organic matter coming down the river and that colored material really has impacts such as associations with metals like iron and aluminum, but also contaminant metals like mercury. And so in soil environments, we have that interaction and that movement, but it does end up in the aquatic environment and has consequences for carrying these different components in the environment. And recent studies have suggested that with wetting of climate, like with wetter climates and more precipitation, we would expect that the water that comes into water bodies and into that landscape of so much water that has all that organic matter and the different metals with it, that when we increase the water in a wetter climate, it's going to move that material more quickly. And instead of the metals and the organic matter basically falling out into the sediments, it's moving downstream. And that has to have consequences when we think about downstream ecosystems. That organic matter, as you noticed in the rivers, you probably noticed when you're around the province looking at rivers that there is a tremendous amount of color associated with it. I'm using a photo here from a spring in Florida because you can see the contrast between the completely colorless spring water mixing with that dissolved organic matter coming from the terrestrial environment. And it changes that environment. So the organisms like these fish here, their environment changes completely. Like the coloration, the amount of light that's available, their ability to, find predators or prey changes tremendously. And up here in the forest, like when we're up in our forest ecosystems, that's where it's coming from, okay? And the changes of the nature of those ecosystems are contributing to that change in the aquatic environment. And so we're all asking various questions about what that might do, and we're trying to better understand the influences in the aquatic environment, but also the marine environment, because that means our rivers are receiving different things because of the changes in the landscapes. We could have physiochemical differences in the water column, reduced light availability, changes in plankton community, and differences in what's there as an energy source. This is a kind of what you typically see when the river water comes into the marine environment, and you see sort of these white lines is the mixing zone between the fresh and the marine, where all these interesting reactions can occur. And we want to know what the consequences are of that. So terrestrial organic matter, I mean, when it hits the seawater or in areas where there's more of it, you can form particles, and those particles can contribute to more sediments in the environment, but it can also pull metals into that as well and deliver that into the marine sediment environments, impacting those. But it also, that change in light environment caused by the organic matter can change what primary producers, that algae that grow in the water column can change, and they typically have been found to become smaller. So you combine the smaller algae and those particles in that water system, and you have a different food source essentially, and also a vector for metals that can get up into higher trophic levels into other organisms in the marine environment. And that smaller plankton and those little particles can really change the food chain too. It lengthens, it makes it so that there's more steps involved and less efficient energy getting up into higher trophic levels in a marine environment. So here there's big connections, between what's going on land, what's being transferred into the marine, into the aquatic environment, and this into the marine environment. And so I kind of wanted to just touch on these different things, because I think when we think about climate change and we're trying to understand where we're headed with respect to the changes in the atmosphere with those emissions from all of our activity, powering our lights and so forth, we have to understand, number one, is that the natural environment that we live in is responsible for taking up a large part of what we put there. So we've really benefited from that. And they're part of these natural-based climate solutions that are being talked about, or mitigation strategies. That are strategies for reducing carbon dioxide in our atmosphere. But we have to understand that, like everything else in the Earth system, these ecosystems that are storing carbon, actively taking up carbon dioxide from the atmosphere, are also responsive to climate change. And as we continue to emit carbon dioxide and contribute to this changing climate, these systems are changing as well. And we need to better understand where they're headed as well in all of this to get a better handle on what we're having to adapt to. So the response that these ecosystems would have are going to be regionally specific. We live in a very wet place, where we probably would expect primary production in our forests to be able to increase because they have the available water to do so with a warming climate. But the form and the intensity of that water will have consequences on the stores of carbon that may be being put into those soils. The water that comes into these ecosystems actually connects pathways associated with carbon movement. It can help enhance natural sinks for carbon dioxide through productivity, but it also can have downstream consequences that we need to understand that could affect the fate of that carbon, but also ecosystem effects that are important to resources in that area. So I touched upon some things that are involved, that my research group is involved in, and I have to acknowledge that this has been supported by a tremendous group of people that I've had the pleasure to work with, as well as others now currently. But lots of folks that span individuals that are in this province, as well as the Canadian Forest Service and folks from away that have worked on this research. And hopefully, with the few folks that are here, maybe we have some questions or things to discuss. I'm hoping that maybe this stimulated some ideas out there. Thanks.
My big question is, do you feel like anything that we do now is going to make any difference at all?
Oh, yeah, absolutely. You mean as far as reduction in emissions?
Yes.
Yeah, yes. I mean, we're married. We are married to a significant amount of change, because what's already there is there, and we're going to be entrained into a changing climate for some time now. But by reducing emissions now will be a tremendous benefit for the not so distant future, for sure. So yeah, there's no two ways around it. We just have to do it.
So Joan asked, what are you encouraged by?
Oh yes, because I did see a chat. Oh, well, and that's part of the reason for this talk here. And I'm sorry it didn't come out that well, but I am really encouraged by the responsiveness of the ecosystems around us. We have an environment that up to this point has been reducing the impact of our emissions tremendously. You know, getting that 50% discount on what we're putting out in the atmosphere has given us a lifeline, if you will. Because if all the emissions that we have put into the atmosphere over the last number of decades or century have all ended up there rather than being taken up by our environment, we would probably not be here talking about it, to be perfectly honest, because things would be so unsettled. Our abilities to maintain a productive society wouldn't be there. And so I am very encouraged by that. I'm also very encouraged by, I think a lot of communities are heavily involved and invested in looking for different strategies and actually enacting strategies. So I'm currently on a panel, a report that's going to be coming out this fall. So this last about 18 months, I was on this panel that was actually reviewing these natural climate solutions for Canada. And albeit, at the end of the day, probably less than 10% of our emissions will be taken care of if we do all of these natural climate solutions and enact these management strategies in agricultural and management strategies in forestry. The net result for the 2050 target is, a help. It's part of the solution. It's not, but we have to have reduction in emissions. But I think that having those processes and management strategies underway and doing the monitoring that goes along with it and having those as part of our normal way of doing things will have tremendous benefits in a longer term sense, because it's going to help us conserve what we're doing with our resources. It will also benefit us tremendously in terms of further understanding what those systems are doing and how they're responding to climate change, so that we're actually going to be able to adapt better in the future. So I'm really encouraged by that, because these kinds of management strategies are already underway. If you look at our agricultural sector within Canada, we're doing a lot already. And so the question now is, what do we do further? Because there are a lot of things that are already being enacted. And there are many countries in Europe and some policies in the US as well. So it's actually quite encouraging. I think we have a long way to go with respect to getting our energy sector emissions down, industry emissions down. But people are getting on board.
What are some management strategies?
Yeah, that's a great question. So with these natural climate solutions, some management strategies, like examples, would be in forestry practices. There are some strategies where you can take and alter the frequency of cutting, and also look at ways of thinning. So some forestry practices would be aimed at reducing the amount of carbon dioxide that's emitted through the cutting process. So you cut trees. What do you do with that wood? If that wood is used for long-term purposes, it becomes a store, and it's actually going to enhance that sink of carbon, rather than using it for another purpose, which might be just releasing it back into the environment. Another part of forestry practice is managing the practices to reduce the disturbance of fire or the disturbance of insects. And that could come about by doing some kind of thinning, or some of the strategies that have been proposed are to mix species. So transfer species from more fire vulnerable to maybe some deciduous, maybe harder wood species that are less fire vulnerable. And if you mix them, they become less vulnerable to insect outbreaks and damage and losses in that way as well. In the agricultural sectors, there's a lot of management around nutrients. And you might ask, like, well, how does like nitrogen or nutrients actually influence greenhouse gases? And a big part of that is the agricultural sector and our activities, just broadly speaking, when we carry out conventional agriculture, we use a lot of nutrients. They are intensive on energy use to produce. And B, when we use a lot of it runs off. And so a lot of nitrogen runs off from these environments and contributes to nitrogen cycling out in the aquatic environment. And that can lead to release of other types of greenhouse gases, including nitrogen dioxide or nitrous oxides. And nitrous oxides in the atmosphere are very powerful greenhouse gases. And when we look at emissions and we talk about CO2 emissions, we talk about CO2 equivalents. So we include things like nitrous oxide. And management activities have been done, like trying to use more precision amounts of nutrients, and also doing things like low till and crop cover, like doing crop covers between harvests. Are ways of trapping that nitrogen and allowing less of it being released into the aquatic environment, and therefore reducing the release of this very powerful nitrous oxide greenhouse gas, as just an example. There's also methane involved in a lot of agricultural systems that's being managed. So lots of really good management strategies that are actually being utilized already today, but more that we need to encourage, I think, to help increase these sinks.
Thanks again, Dr. Ziegler, for spending some time with us this evening. And I found it really hopeful. Like you're,
I'm glad, because I think there's
cons-
a need for that, right?